Welcome to another exciting version of E301. Today we're going to be talking about capacitors and inductors. So I'm going to get right to it. I'm going to share my screen and we start with, all right, so we've got capacitors and inductors. We're going to define capacitance, stated symbol and unit of measurement, predict the capacity of a parallel plate capacitor, analyze how a capacitor stores charge and energy, explain and analyze capacitor DC characteristics, define inductance, so we move into inductors, define inductance and state its symbol and unit of measurement, predict the inductance of a coil of wire, explain inductor DC characteristics, again DC, and then analyze how an inductor stores charge and energy. All right, so first thing, capacitors and inductors. For resistive circuits, the voltage current relationships are linear and algebraic. Resistors can only dissipate energy. Okay, so that's why it asks how much power is absorbed by a resistor in most of our questions, but resistors can only dissipate energy. Capacitors and inductors, they store energy. Okay, so they store it. Capacitor. Capacitor is a passive element, just like a resistor. They're both passive. Okay, it's a passive element designed to store energy in its electric field. Okay. Capacitors often consist of parallel plates separated by an insulator or dielectric. So, like the diagram here shows, you've got the two parallel plates and some dielectric. In this case, it's air, although often what we use is some plastic or something like that to keep it apart. That's not lead, that's lead. Okay, so that's the connection points. So it connects someplace in the middle of the metal plate. And you got to think that, all right, if that's the connection point, then it's got to spread out the current and charge across those plates, which leads to some resistance, but that's okay. So, definition of capacitance. Capacitance is a measure of the capacitor's ability to store charge. Okay. Now, the relationship between capacitance and the charge and the voltage is given by C equals Q over V. Okay. Now we can rearrange that to be Q equals CV, right? Well, then if we take the derivative of both sides, which we aren't going to expect you to do, so that's dq dt is equal to C dV dt. So we take the derivative of both sides with respect to time. Well, interestingly enough, dq dt is I. So I equals C dVc dt. Now, we don't need to remember that because, fortunately enough, that equation is right here on the equation sheet. So you got IC of t is equal to C dV dt. All right. Now, do we really need to use that very often? No, not often. But the point is, all right, the capacitance of a capacitor is 1 farad. So that's named for Michael Faraday. The abbreviation we use is F. Okay. So a farad stores 1 coulomb of charge when the voltage across its terminals is 1 volt. All right. So we won't worry about that example. We'll move on to how do we calculate capacitance? Well, the capacitance of a parallel plate capacitor is given by C equals epsilon R, epsilon 0, or epsilon naught, A over D. So the area of the plates divided by the distance between the plates. So it's the distance between the plates, okay? And the epsilons are, epsilon R is the relative dielectric constant of whatever the dielectric is that's between. Epsilon naught, that is the dielectric constant of free space. So it's 8.854 times 10 to the negative 12. So we measure that. That's what we've found it to be recently. So A is the area and D is the distance between the plates. All right. So we're going to move on. This gives an example, and it's mostly a discussion of conversion of units from inches to centimeters and meters and stuff. So I'm not going to worry about that. What we are going to worry about is capacitance in steady state. Okay. So in steady state DC being constant stuff, All right, so in steady state DC, the rate of change of voltage is 0. So going back to what we were talking about before, we said, all right, we've got this equation, I equals C dV dt. Well, if dV dt is 0 and C is some capacitance, that means the current through the capacitor is 0. So what kind of component has 0 current through it? That is an open circuit. Okay, so at steady state, a capacitor is an open circuit. And if we treat our capacitor as a Thevenin load, we can find this would be VTH and this would be RTH. Okay, so the capacitor is usually, when we're trying to figure out what's going on with it, we treat it as a Thevenin load. We find the VTH and RTH that lead up to it. Okay, so we'll do that later on when we're trying to figure out things for when things are changing. All right, but for right now, we'll talk about power and work for a capacitor. All right, so the energy or work stored in a capacitor's steady state conditions is given by the equation E, or W, is equal to 1/2 CV squared. All right, and the units for that is joules. Now I could derive this for you, but that's not going to be very helpful. So now the question is, if that's the energy, all right, and power is energy divided by time. So once that starts, being time, all of a sudden the power becomes 0. Okay, so that's an important point. All right, the power dissipated by a capacitor is 0. All right, that's real power. Now we're going to talk about inductors. An inductor is a passive element also. All right, so it's a different passive element, but it stores energy in its magnetic field. Okay, so the capacitor stored in the electric field, the inductor stores it in the magnetic field. And you can kind of think of a capacitor as, like a pressure vessel. So it holds the potential, kind of like, you take something up to the top of a hill and all of a sudden it has potential. That's what a capacitor does. Meanwhile, an inductor, the way to think of that is you think of it in terms of momentum. Okay, so once you start getting something flowing, something moving, all right, it resists the change in its momentum. So if you have a current, okay, that's a flow of electrons. Well, the inductance is what causes the momentum to stay constant. Okay, so that's the kind of concept that you can use for thinking about this. So you need to create an electromotive force or a voltage in an inductor in order to change the current. And the way that's related is V equals L di dt. Okay? Now, you can think of this in terms of, so something interesting about this is that L, is equal to V over di dt, right? But C was equal to I over dV dt. And how is R, V, and I related? R is V over I. Okay? So if you have a bunch of resistors and a bunch of inductors, the resistors and inductors will be accumulated similarly. Meanwhile, capacitors, they get accumulated in the inverse method. So you can work that out from how these equations are, right? So this is for a capacitor, that's for an inductor. This was the energy for the capacitor that I mentioned up above. And we'll later get to this one, which is very similar and looks the same. So, but first we'll talk about, all right, L is the inductance of the coil, and the unit of L is the Henry. Okay, and that's abbreviated with an H. the inductance of a coil is 1 Henry if changing its current at 1 ampere per second induces a potential difference of 1 volt across the coil. All right, so they figured out how to make that all work. In terms of an inductor's physical characteristics, so if you're going to use the physical measurements and stuff, you've got a coil like this, right? It's got a certain number of turns, so that's the turns. Okay, A is the area of the coil, and L is the length of the coil. Now mu, this mu, is the permeability of air times the relative permeability. Okay, the permeability of air is equal to 4 pi times 10 to the negative 7 henries per meter. Okay, so that's what you would use if you're trying to figure out what the inductance of a coil is if you have the measurements of it, right? So that's just kind of a background type thing. So inductances and steady state DC, all right? In steady state DC, the rate of change of current is same as the rate of change of voltage. This rate of change is 0. Therefore, the induced voltage across an inductor is also 0. Well, the voltage, a 0 volt thing is a short circuit. So a capacitor looks like an open circuit, all right? And an inductor looks like a short circuit. Now, an easy way to kind of picture that is if you look at the symbol that we use for a capacitor. So let's go back. The symbol that we use for a capacitor, there's a gap there, okay? So in steady state DC, that gap just gets wider, which leads to an open circuit, right? In steady state DC for an inductor is just a coil, which is a wire, right? So in steady state DC, that just kind of straightens out and becomes a short. So that's how you can remember it from the drawings, right? So in DC, they do exactly what their drawings look like they do. Now, inductor energy storage. An ideal inductor doesn't dissipate power. Power applied to an inductor is VI, and we saw previously that the voltage is L di dt. So P equals 0 watts, and E equals W equals 1/2 Li squared. Okay, again, this is in joules. And again, that's on the equation sheet, right? So once you find the current at any particular time, right, that's how much energy is stored in that inductor. So the current at any particular time is the energy stored in the inductor. The voltage at any particular time is the energy stored in a capacitor. With that, I'm going to move on to one example which uses both a capacitor and an inductor. So we're going to determine the current I sub L and the voltage V sub C for the circuit shown below. So this is a circuit analysis problem. So we start off with, all right, we've got our circuit here. And the next thing we do is we circle the nodes so that we know where all the nodes are, okay? Now, these are all the nodes. So that's what the nodes look like. Now, next thing we can do, what we should do next is redraw the circuit. Why? Because there's no switches in here, and this is a DC source. Okay, so we're going to redraw it. I'm going to say, all right, this is a 10-volt source. We've got a resistor that is 2 ohms. And we've got an inductor here. And we're going to try to find out what the current is, I sub L through that. And below it is the 3 ohm resistor. Now, so I drew the short for the capacitor, for the inductor. So now for the capacitor, I draw the open. And we say plus minus VC, right? And we've got this 4 ohm resistor over here. Now, the question is, with this 4 ohm resistor, is there going to be any current going that way in steady state? No. The current there is going to be 0. So if the current there is 0, what's the voltage across? Well, it's going to be 0 volts. So this node here is going to have the same value as, we have this as ground, this node, which is at 0 volts, right? So we've got, now we can draw all of our nodes like this, and we've got this node's at 0 volts, and because there's a 0 volts difference over here, that one's at 0 volts, this one's at 10 volts. Now, we look at the rest of the circuit, and we say, all right, here's a 2 ohm resistor, it comes into this node, no current, that current there is 0. I equals 0. So there's no current going that way. All the current has to go this way, which means that these two are in series. Okay, so if these two are in series, then you got a 2 ohm and a 3 ohm. They add together. So we've got, for our current in the inductor, we've got our voltage divided by the R series. Okay, and the voltage is 10 volts. R series is 2 ohms plus 3 ohms. Right, so 10 volts divided by 2 ohms plus 3 ohms, that's going to give us 2 amps, right? Okay, now we've got the 2 amps there. Well, if there's 2 amps going in IL, VC is over here. VC is between this node and ground. So what's the voltage there? Well, VC is equal to, we can call it node A. I mean, you can do it any number of ways. Current through there is 2 amps. So that's going to have 4 volts across it. And this has 2 amps through it. So that's going to have 6 volts. So VC is between node A, which is at 6 volts. So 6 volts minus 0 volts means that we've got 6 volts. So VC, that is IL times the 3 ohms, because this VC is in parallel, even though there's 0 volts there. It's essentially the same. It's on, you can consider it in parallel. So that's 6 volts. All right. And that's what we have for capacitors and inductors. Thank you for your time. Talk to you next time.